Okay, dear ladies and gentlemen, we are starting our next stream. Finally, this is the first stream of this week, and we are continuing this series about special electronic configurations and special two-dimensional materials. And today there will be an article which is written by similar authors of the previous article. So let's just jump to it, since I don't have some really good preface. So again, the same format, that we have this wonderful application here that will help us to do this presentation. The article is called Non-Equilibrium Quantum Domain Reconfiguration Dynamics in Two-Dimensional Electronic Crystal Experiments and Quantum Simulations by a lot of authors, and Jaka Vodeb is the first author. Okay, let's start with the good overview, which I forgot to prepare. Yeah, unfortunately I need to think about it right now immediately, because I forgot to show you what is the impact of this article, which is not really important in terms of science, but it's important in terms of general understanding. So this article has 8 citations, and it was published in 2021, first time. So all these discoveries were in the 2021, but then after only 3 years it was accepted to the journal and finally published in the journal in 2024. Okay. Okay, so that now you know how impactful this article is, and okay, today we will try to figure out what is the real value of this article. I hope at least one person will ask me something, but if no, then anyway, I'm absolutely fine. So, okay. Let's jump to the main takeaway of this article, and then we will go again through each statement. Okay, through the majority of the statements, not through each of them. So this article is around 5 pages in the Nature, but then it has a lot of supplementary material, and supplementary material is around 30 pages. Okay, it's 37 pages, but there are a lot of citations which we don't really count as a page of information. So okay, so totally the volume of the information is very big. That's why I wasn't actually thinking about everything what happens in this article, but I thought I should reconsider this format, because it's impossible to read everything, understand everything. So maybe later I will not focus so much on understanding really everything, but just read article and maybe look sometimes at the supplementary information, and not try to understand like 60-70% of the supplementary information like I did in the previous stream. So the essence of this article is the following, that if we have, okay, everything here is about tantalum disulfide. Here there is the road to dimensional electronic crystal. But actually, as far as I understand, everything here is only about tantalum disulfide, and nothing here is about something else except this material. So if we use STM measurements, and what is STM measurements, we can see, I mean, that's just a tip of a microscope, but there is also illustration of this tip here. Let's move it here. So that's how it works. Okay, that's the heat map, but there is this microscope which was created by clever people who knew how how they can measure electronic configurations by how much current flows from the material to the tip. So okay, we will not go into discuss how this microscope works, but somehow with this microscope, if we use this microscope to analyze tantalum disulfide, we get this experimental picture. So what is shown here, that turns out that electrons here are localized in some balls. Okay, there is a lot of theory about such balls. They're named polarons. We can discuss for a long time, are there really that polarons that are meant here? Or maybe it could be a charge density wave and something else. But okay, for now, let's just believe that these are polarons. Anyway, we can use the word polaron as just a synonym of localized electron. And for some reason we say that here there is one electron per this ball. Anyway, okay, it's actually a good question why exactly one electron corresponds to one ball. I will write this question for me. Okay. Okay, so anyway, as far as I remember, they claim that there is only one electron here at the peak of the intensity which was obtained by STM measurements, and there is some configuration of the electrons. That's like one area, that's another area, another area, and another area. And that's why there are colors, because they just highlight the same configuration. It's actually interesting that, yeah, like maybe it's related to the statement of the ground state, and further in the article they will tell us that there are 13 ground states, but out of this 13 only 3 are there. I'll write myself a question about this ground state. Okay, that's a good question. How do we know that there are different ground states? Maybe that's the same ground state, but there is just a wall. If it was the same, then why would we have wall? But still not clear why do we have different ones, because they look very much the same. But anyway, we have walls, we have some ordered regions in between these polarons, and where walls, I'm not sure what happens. Maybe there is a hopping of electrons, or there is just no electrons. Maybe both descriptions are valid. But okay, so idea is that like time passes, and actually a lot of time passes, as we will see later. 10 to the power of 3 seconds, and I'm lazy to convert it in minutes, approximately passes, as far as I remember, and this configuration changes to this configuration. Then again we do the same measurement, but after next shift in time, and we have this measurement, I mean this configuration. Yeah, okay. I will write myself also a question that right now I don't see really a relaxation, and is it always true or not? Yeah, okay. Just interesting here on this measurement that we see that transfer from this to this doesn't look really like a relaxation, but we expect to have a relaxation. And by the way, I didn't mention it, but you could ask an important question, like how at all we can get this initial configuration, and it's obtained by some injection of electrons, for example, from the tip. How exactly it is done, it's not written in the article, so I don't know, but I tried to find answer in this question. So somehow we inject more electrons, and then I will write myself a question, what happens with this electrons? Okay, so maybe these injected electrons go out of the system. Yeah, so I wrote myself a question that maybe actually like after injection of electrons, the number also decreases, and I don't know what to say about it, because looks like it just increases because they become more dense. Okay, so it's not clear what happens with these charges, because you might say, like, look, here we have domain walls, there are no particles in between, but after this reconfiguration we have no domain walls, so there are more particles, so they should not decrease but increase in their number. I don't know how to answer this question. Maybe indeed they come to the system from surroundings. It could be. Anyway, the system is open in the sense that it interacts with environment, which then gives us this dynamics. So this dynamics, as far as they write, originates from two reasons. The first reason is the quantum dynamics, and another reason is the thermal hopping. And by quantum dynamics, I mean because of some quantum fluctuations, because everything is quantum in this world of nanoscale sizes. And they discuss in this article further what is the real origin. I don't think that they came to a good conclusion, but we're here for a long time, so maybe soon we will get some answers on this question. Anyway, okay, that's the measurement that they have. Then after a lot of words in the introduction, they say that that's the model which they believe in. Where they have the screened Coulomb interaction for the sites, because they have studied already this material and they checked that such screening potential makes sense. However, there are a lot of questions about it, and you can watch the previous stream where I discuss how useful this term is, and the conclusion is that actually there are really a lot of serious questions about this term. But here they say that, okay, this model is there, it makes sense. I mean, the extension of the previous model. Right now we also have two extra terms, the kinetic term and the chemical potential term. So nothing much is discussed about them. They are just there. And wait a second for me to take some water. So the terms are there. The meaning is approximately clear, that here we have different sites, we have sum over the neighboring sides, and this is hopping from one side to another. So like, of course, we work in this second quantized formalism, which was introduced somewhere in the basics of condensed matter. So right now there is no sense to comment this formalism at all. It's the well-used formalism. So the Hamiltonian is operator. It acts on the whole system. I just noticed this index m, which I forgot about so I'm not sure about the meaning of this index m. They will write below also energy with index m, so later we will look more carefully on this index. But that's the initial point. For some reason we have this minus here. I'm not sure why there is the minus here. Maybe I didn't write this question. I wrote other questions. But anyway, that's the kinetic term, which gives us hopping between one side to another. For example, okay, we need also to say that there is an atomic atomic lattice, and there is a superlattice of electrons. And here by I and J we mean that, okay, it's also a good question. It's a good question that maybe they meant atomic lattice, and these electrons, they sit in this lattice. Also, there is this typical question that maybe the electronic lattice distorts the atomic lattice, and maybe we should have some changed sides, but let's neglect this effect. It looks like an effect of the second order. Okay, the minus I can't explain. I and J I explain as just this fixed lattice which doesn't move, because it's already complicated even if it doesn't move. Then there is the potential term which tells us the energy of nearest neighbors interactions. So we say that there is particle on one side, particle on another side, and that's the energy. If they are both present, then these numbers are 1, and we have this contribution to energy. Q should be equal C, and Q dagger should be equal C dagger. We don't have a Q dagger here, but we'll see below this model. Then this chemical potential term is also rather typical. Unfortunately, I didn't think much about it, so let's just pretend that we always see such terms. So yeah, like I was thinking several times about this term, and I have not good understanding about the nature of it. I mean, because we can say typical words that look, we can shift chemical potential, and this determines us the Fermi energy, or how many particles are there in the system. But like, what I want to see is the strict derivation of it. Or should we take, I don't know, like consider this as a free energy or grand canonical potential? Like, why at all? Yeah, I mean, that's what happens when you work with articles for a long time. You already starting to forget some things that were obvious for many years. Because, like, of course, there is the chemical potential in the Hamiltonian here and in many other places, but it originates from grand canonical ensemble, and in grand canonical ensemble we have the omega. but I'll double check it. That's definitely a correct formula. I just forgot this term. So that's the Hamiltonian that they believe should explain the system because of common sense reasons, and also they have this term in the previous one of the previous articles, so that's this term definitely makes sense. And if we add these two terms, then maybe nothing bad will happen. Maybe this term will give us the dynamics of the walls, domain walls between regions, but maybe no. It's also another good question. Okay, maybe that's the kinetic term, because maybe without it there would be no dynamics. And okay, that's the initial model. Then they say that actually transverse field easing model is useful for some materials, and transverse field easing gives us the motivation to use the quantum computer. So this article, okay, one of the maybe main values of this article is that they say that they have used quantum computer simulations to get something useful about the nature and especially about these measurements. So to use programmable quantum computer, they like initialize state somehow, and then they use another version of the Hamiltonian which governs the evolution, and that's the Hamiltonian, which is like which corresponds to programmer quantum annealer. That's how they call this model, which is employed in quantum computer. For some reason there is also temperature and the effective temperature, and there are some discussions about the effective temperature, but I don't remember it. The main point is that somehow, in order to use quantum computer, we need to initialize Hamiltonian and plug initial parameters to it. And here, if they want to simulate the dynamics, they somehow, how to encode, by the way, initial state. Okay, so that's what I don't understand, but somehow they encode this initial state. So maybe by state we mean the position of each qubit. Yeah, so somehow I don't know, I wasn't thinking about it, but somehow they encode the initial position into the qubits, and that's the Hamiltonian that governs evolution, with a lot of other complicated features which we will meet soon in this section. Quantum simulation of domain reconfiguration dynamics. Here I just wanted to extract key information for people who value their time to grasp main idea and be happy with understanding main idea, since anyway this stream will be at least for 2 hours. I'm not sure how long. But that's a big article. They have, as I announced, more than 30 pages of supplementary information, which is essential for understanding of like value of the research and how exactly it is done. Like you see here that they do quantum computations on quantum computer to get some value for real world. So if you think about it, that like how to use quantum computer and how and which value you can get about the real world, that's already a big question. So you can imagine a lot of things that they can write in their 30 pages. So of course I wasn't reading all of them. I'm just aware about some pages there. And maybe today I will read something right during the stream, but usually it's a bad idea because it takes a lot of time to understand this. So the preparation for the stream was about 10 hours of my work, by the way. So anyway, that's the model that they believe in. That's the version of this model on the quantum computer. Somehow they do this simulation, and don't ask me how, because I wasn't working with quantum computation, so I can't tell you anything about it. But that's the results which they got. That look, we can initialize state, and then we have some time. I just understood that. I also don't know how this TA, which is used, okay, we will see that T is used here in the parameter S, and the parameter S is used to set the Hamiltonian to the proper value. So, okay, I'm not sure about this little t. It looks like time, maybe annealing time with this index A, but I wanted to understand how this time is compared to the real time, where we have minutes, but there you have microseconds. So yeah, it's not clear here how this time is related to time in these pictures, but if you read articles it will be maybe also not clear. What is R is maybe this one parameter here, which is multiplied by potential energy and some shift term. And why effective temperature is like this, I also don't know, but we expect them to have some low temperature. Okay, I will write myself another question. Yeah, so some parameters are present here, but somehow they do this quantum simulation, they get this. They get these results with some white islands. What is the origin of white islands? I absolutely don't know, because it's rather detailed. But that's the result of this simulation, and they have several plots. I have chosen only this one out of others. So this essential thing is that okay, they also connect this parameter to other parameters, but even without this connection, which is not as explicitly written as it could be, they consider so-called reconfigurational rate. Why do they consider reconfigurational rate? It's not clear. Okay, but there are some definitely ideas behind this parameter. It's way easier to explain what this parameter means in terms of formula than to explain why exactly this parameter is used. So what happens? Like we have some time slices, I guess, and each slice some number of polarons can be changed, and we count these numbers, we count them before and after, so then we divide by the total number, and that's the reconfigurational coordinate, so called, which is named by little f, and we will see this coordinate, this little f, throughout this article. So reconfigurational rate is an integral, so we sum all of these rates of all times, I mean, which is denoted here as integral, and we divide by delta t. And okay, I forgot actually. Maybe delta t is the same as tx, which common sense hints us, because that's like typical normalization. There should be something else in this parameter, in this definition. So that's how they obtain this reconfiguration rate, by this formula and by borrowing, but some yeah, extensive computation. So they put the configurational coordinate to this formula, get the reconfigurational rate, and then they plot it as a function of 1000 divided by t. I'm just thinking first time about it this carefully. So is there sense? Okay, it's a good question. So that's how they do it. I think right now that's a bad idea, but I wasn't thinking enough about it. Here they have a big scale. Why do they multiply by 1000 and then have such a big scale? They could have multiplied by 10 and then have a scale from 1 to 2, not from 100 to 200. But okay, even that's not really important. The important thing is that there is this rate and this parameter, and that's the parameter that they choose to look at, and they compare it from quantum simulations, from this model, that strange simulation, and the experiment, and the result is that, oh, they coincide, which confirms that quantum simulation is a useful topic. Basically, that's the main idea of the article. As it's written in the even title, experiments in quantum simulation. So that's the experiment. Yeah, the charges are reconfiguring, and simulation also tells us the charges are reconfiguring because everything yeah, because like as far as I understand, here there is also noise somewhere in the system. I just thought that maybe one of the ideas here is that like quantum simulations on noisy quantum computers are really good, because exactly by noise we have such reconfiguration. Here we have again reconfiguration again by noise, and maybe noise has two contributions which were announced before, the thermal one and the quantum one. And right now I don't really remember some good theory about all these noises, because I was like learning only one theory a long time ago, and this theory was very, very unapplicable. at least right now. Okay, I'm very motivated. Okay, I'm motivated to show you this theory because I approximately remember it, but it will lead us too far away from the article. And the conclusion from that theory is that there is like correlation between like displacements of atoms of lattice because of like two types of fluctuations of thermal and quantum, and that's all. Like they don't explain how it can be applicable, so yeah, it's a good idea to do Yeah, so that theory unfortunately is not working here, so instead of good comments I can't tell you much, but maybe because of these two types of fluctuations and only because of them, and not because of environment, we have this reconfiguration. And here maybe exactly because of the noise in the quantum computer, they have this reconfiguration, and they say that this has similar rate, which for some reason proves that this quantum computation is a good one. Yeah, it's actually a good question. Okay, another good question which I just wrote is that actually after spending more than totally like 20 hours in this article, but right now for preparation I was spending only 10 articles, like other 10 were spent maybe half a year ago or even in November of last year, and today is the middle of July. So after 20 hours, I still don't know what I mean right now. Maybe during this reading I will understand it, but right now I don't know what is the valuable insight. Yes, this reconfiguration match, that means that this model is applicable with some very tuned parameters. Yeah, actually, it's also a good question. So, yeah, I think as far as I remember, they really tuned these parameters. Definitely, they tune RS, the R, and they discuss this R. As we can see, there is also effective temperature, which they also tune somehow. I'm not sure if it really coincides with the experiment, but okay, the question is that there is second parameter, so but I think that the point is that they really tune these parameters and say that actually this result coincides. So the question is that what is the valuable insight for this material? What can we tell about this material? And I don't really remember. So let's read the abstract, and after reading abstract we'll do a little break because it will be a good pause checkpoint to have a like 30-second break. So let's read their abstract and discuss it. I propose to just skip this sentence because that's not really a useful sentence. I'm sorry guys for this loading. We don't have still a developer for this app. That's a very active field of the research because of some motivation that is always there. No, I don't think that there are some fundamental aspects of many body non-equilibrium quantum physics. I don't know any. If you know, then please write in the comment. But no one will write it, so meaning that no one also knows, or no one watches this video. Okay. They also say about some topological constraints. Yeah, I mean, we can also skip these words because it's not explained here what do they mean by topological constraints, but as they usually say, classical dynamics is the I mean, they always need quantum computers to do some quantum computations. Without quantum computers, they complain that classical computation is too slow or something else. However, there are some methods of classical computational physics, and I don't know what's going on there, but in this article, they will just use the quantum computation, and that's all. So okay, it's actually interesting. Okay, so so here they claim that dynamics okay, they don't dominate it. Yeah, so here like let's look at the final result, because that's what they mean when they write this, that look, like there is the parameter that changes, and this parameter reflects how much domain walls are changed. And here we have a temperature dependence, here we don't have a temperature dependence. Okay, I just understood first time that actually here quantum simulation ends, but it's not really the temperature independence. It's again question. Actually, I have already approximately 2 pages of my notebook, which is A5 format notebook, but still they're written full of questions. So here we see that actually there is, like, it's impossible to tell that there is no temperature dependence or independence, because we have just two points. Why wouldn't we make more points? Maybe it's not that hard if you do the quantum simulation. But that's what they see, that this is the crossover. Somewhere here there is temperature dependence, temperature independence. These are the thermal fluctuations. These are the quantum fluctuations because of like temperature dependence or temperature independence. And they say that some environmental noise makes this change. And this is investigated also by these microscopic techniques. That's how we should understand it. Why it's written in the context of experimental noise, I don't know, because environmental noise, because okay, it's not clear how environmental noise at all fits to this picture, but they have some discussion about the Logaric model, so later we will try to understand it better. Yeah, here they say what they also said, that this is the model that's called quantum annealer or simulator. Doesn't matter what these names mean. It in general, that's the name of this model. Yeah, and that always happens there, so I don't know why did they write explicitly it here. Okay. Then they have some terminology which I am not sure about. Here we see that there is a notion of pink noise. There is also 1 over nu noise, and is it the same or not? I don't know, because there are a lot of questions and I wasn't answering this question. But they say that there is the same noise in both simulation and experiment, which they call pink noise. So that's what they write here, that reproduction is a good one. Then they claim that it led to better understanding of noise-driven quantum dynamics, but I can't recall any better understanding. They just say that, hey, this model is applicable, which maybe is not very strange, because it's very expected that after some time, it's a very strange plot. That's what I see only now, that look, f depends on time. Time passes and we measure f, but that's like the total change of the particles. And here we have rate as a function of temperature, not on time. So how many of them have changed if we have this or that fixed temperature? It's actually 1 over t, but it doesn't matter. So if we plug big T, what will it be? It means that we are somewhere here, and at big T we have big number of changes because of these thermal fluctuations. If we have little t, then it means that we are somewhere here, and at little temperature there are not so much fluctuations of polarons. That's obvious, right? Like that's very expected. Okay. It's also not really clear, and I noticed it only right now that they have different scales, 10 to the power 8 and just 10. And I don't remember that they commented much about it, but that's very strange, because when I expected them to have approximately similar scales, maybe they wrote something about it in supplementary information, because I don't remember explanation of this in the article. But here they say here that reproduce, that's what they mean by the reproduction, and they gave them some insights which I can't recall right now, and I don't remember that these insights are written in the article. Well, this says about extraction of some parameters that correspond to tantalum disulfide, which is analyzed here in the model. So but okay, that's already written here, this question, which I don't understand, about what did they understand better. Okay, they again related to non-violet memory devices, as they wrote in the previous article, because they really like to mention memory devices. Then again, there will be a citation which no one will look at. They haven't looked at it, but maybe after several streams, I'll finally look and understand what finally does it give about memory devices. And that's the material that will be analyzed. Only this material will be analyzed. Okay, it's also an interesting question that here in the whole abstract, which we have read recently and discussed recently, this crossover, I should delete this question. It's not a question, that's the crossover. But here nothing is in this article written about other materials, so why did they choose at all this? Yeah, it's not really clear why did they choose exactly this material, but somewhere here, I mean, here is nothing written about it, but in this whole article I didn't see anything related to other materials. So now you know in general what happens, that there is a measurement, there is a simulation, they coincide, and they promise us that there are some important conclusions from measurement and simulation. I don't know which, but we have just begun. So stay with me and let's have a break for like 30 seconds or something. Okay, let's finally continue this very interesting activity, figuring out what they have discovered in the article. And okay, we are coming to some little restructured version of the article. Of course, the conclusion goes at the end, but my idea was to extract most important information. And the conclusion here is very nice. It's not a big one, so I decided to just put it here and have it right in front of me. And I think we will go through it rather fast, because maybe to some extent it repeats the introduction. So let's read what they wrote. It's actually really not clear what is the motivation of what they are doing, because yeah, they claim that they can't be explained by classical processes, and there are explanations, I mean comments, what do they really mean, that this rate, I should move it here, this rate will be different if these were classical processes, but okay, of course it goes beyond the article to discuss like why there are such classical processes that do not give us I mean, which exactly this classical process can be used to explain this dynamics. They just have citations, which maybe I will read later. But right now they move forward. They not only say that, hey, we have a different dynamics, that's why classical simulations, classical processes are not applicable. They also say that there is some relaxation which is topologically inhibited, and that's what I don't understand at all, because because I don't know what is it really meant here. There is citation which we can read, but of course no one will read it because there are, I don't know, a lot of citations. Doesn't matter how many, definitely more than 50, because even here there are 44, 47. Okay. Okay, they again claim that there is some conventional quantum decay. What is the conventional quantum decay? Yeah, it's not really clear what they meant here. Maybe some conventional quantum process also not applicable here, but right now they also don't specify which exactly processes are meant at all. So that's why they decided just to use their great, very advanced quantum computers. And just do the simulation, because maybe the idea is that nothing really works. Quantum materials, quantum approaches doesn't work, classical approaches doesn't work, but this simulation works. Maybe that's what they mean. So they say that noise is present, the same noise here and there. Yeah, so actually I have a nice here section about questions where I have some mic questions, but there are really a lot of them, so it's better to write these questions somewhere here. Even here there are a lot of questions, but they are separate. Here there are only separate questions, and that's why I don't write right now the questions here. I will just write it to my note, which will be more reliable than this app, which is not really finished in scope of development right now. So see, despite that it's not clear how they relate, what is the origin of the noise. Maybe because of the R of t. Yeah, so the origin of the noise is not clear, but maybe it's related to this parameter, I'm not sure, but there's the same noise here and there, which doesn't mean much important for us. Yeah, and how could it be another way? Okay. But there's the statement about the noise. that they really want to find it out, and they have found out. Let's read what they write next. Yeah. Yeah, that's about the simulation, that they have the only one parameter R. That's this parameter in the Hamiltonian. TF, effective temperature, is somehow set to be constant. Okay, it's actually not clear why. Okay, that's the statement that I don't understand also, because here we have two parameters, R and T, and here they say that simulation is with single adjustable parameter R. It's not true. I think they have two parameters. The R is here, which by quantumness. Okay, that's the statement that. Yeah, like that's a very bad statement as far as I remember. But the idea is that if R is big, then this term is much bigger than this one, and they say that that's the quantumness. And here there's the kinetic term, which is way lower. So that's like a classical term, and I had discussion of it some time ago, but I don't remember right now much why exactly this is quantum, but why this is classical. I mean, I remember some arguments which I didn't like, so I don't have a clear enough myself explanation of this statement, but that's what is meant here. So one of the motivation of today's discussion is to understand what is finally they are trying to get from the such simulation, and maybe this next sentence can give us some hints. How phenomenological relaxation. One second, I'm a little bit distracted. Okay, now I'm not distracted anymore. So they say phenomenological relaxation rates emerge from microscopic interactions. So look, phenomenological relaxation rates, that's what they mean here. How they emerge from microscopic interaction means that they are modeled by this. But like, that's the simulation. I don't agree with this statement, because we don't get any insight. We just see that, yeah, like if we do this quantum simulation, which they describe technically in technical section, so like how do they initialize state, and then they have some measurements, but I wasn't reading this part of the supplementary information. So so we just see that there is a simulation which is done, which coincides, but that's also already was said before, and we don't see any insight. I don't yet right now know any insight. What is usefulness is just a repetition of what they wrote here, that nothing is important in this sentence at all. Now they announced that it can be also applicable, which is absolutely not related. And I mean, something can be also used well, you can forget this statement. That's for a broadened view, and no one will be discussing it seriously anyway. Just a collection of citations. Nothing is really worth of discussion. Yeah, again, there are like low temperature memory devices, and maybe finally I will read and understand if it's really needed there or no, but right now we just see again this mention of the memory devices. And again about memory devices. So the summary of the conclusion is that they did the simulation, they see this crossover, they get somehow noise dependence, and they're really fascinated about the noise dependence. Then basically they say that there are some relevant topics. So what did they tell us about the nature? Approximately nothing as far as I remember, but that's just the conclusion. So in order to figure out if it's true or not, we need to read the whole article. And we start this not easy journey, as usual, by long introduction, where they will tell us a lot of things which are not related, but that gives us broader understanding. And if you read a lot of introductions, then maybe it will be not that hard to read the next introduction. Okay, let's go sentence by sentence. Yeah, like sometimes after some phase transitions there is an homogeneous intermediate state. That's an abstract statement. You can think type 2 superconductors, which sometimes at some temperatures have some vortices where there are some normal part of the material, and there are some normal currents there. I mean, I don't have a lot of examples to explain better what happens here, like why through second order or symmetry breaking phase transition they end up in homogeneous intermediate states. Like if we look at the typical superconductivity of type 1, that's not the case. I was told about magnetization that there is also second order phase transition, but okay, common sense tells us that nature is very different and there are a lot of different models. That's why this could be the case, but that's just an abstract statement. Oh, that's here a very unclear statement which I don't agree. So I don't agree with this statement, and anyway this article is not related to superconductivity, so you can even neglect this sentence at all. So they say that fluctuations in phase, or like superconducting phase, force causally unconnected regions evolve independently. That's not what I agree with and not what I learned before. Yeah, there is a theory of fluctuations, which is a big one, but it's another story what happens in the fluctuations, and that's not what I know, that there are some causally unconnected regions. I don't think that there could be causally unconnected regions, because causality originates from special relativity, and here we have just superconductivity. And they related to vortex structure, so of course no one will seriously discuss these sentences from the introduction, but no, I don't agree with this statement at all. Okay, let's just forget it, because that's the most useful thing what we can do with this sentence. Then they discuss first order phase transitions. because they said something about the second order, but now they're discussing first order. But anyway, we should keep in mind everything here, because this introduction just distracts us, and that's the essence of the article. Both second to first phase transitions maybe are irrelevant for this domain reconfiguration. They just give some description of the first order phase transitions. Okay, then there are other transitions like topological and jamming transitions. What do they mean by these transitions? It's not clear, but I bet that's irrelevant. Again, they continue elaborating this topic. Okay, let's continue. I just wrote myself a comment about this. Another unclear sentence that kinetics is primarily diffusion driven, and metastability arise from symmetry topological constraints. So here it means that if something changes, usually it happens because of diffusion. What do they mean by classical systems? It's not clear, but maybe they meant some gases. Just like you open like a hole and one gas penetrates another one, then usually we speak about diffusion, and maybe that's what is meant here, that there are some diffusion driven processes. Like if we speak about classical systems, I haven't heard about any topological constraints in the classical systems, but they claim about some metastability. What do they mean by metastability is also not clear, but like maybe stability of a new phase, but now we have a metastability. That's what is not clear, but again, it's not really important. So here, that's a relatively important statement that, look, if we have quantum systems, then two things can happen. First of all, if quantum system evolves by itself, then there is a coherent quantum dynamics. But if there is some interaction of this quantum system with something else, as it's written here, noise-assisted processes. Okay, we can of course understand it from the common sense that there is some like something hits the system from external part of the world, then there is incoherent processes, and by incoherent processes they mean even exactly the tunneling, because usually the potential is fixed and there is some particle inside of this potential, and if it changes the state, then usually it goes from one potential well to another. That's why they say that this can happen, like the tunneling can happen. And by incoherent, it means that, okay, it's not really clear. I'm not sure what it's meant by really the word incoherent, but the idea is that noise can also change the system. And that's what maybe we see here, that because of noise, this dynamic happens. But I'm not sure, is it because of noise or because of noise plus a lot of other factors? We will look below and try to find the answer on this question. No. Okay, that's what they also say here, that they measure it, this state reconfiguration, it was this state, it became this state, they count the polarons and they compare simulations. That's what they do. And they just elaborate this idea and say that they want to identify mesoscopic tunneling processes. However, before there were macroscopic tunneling and not mesoscopic. And I mean, it's like abstract statement. I mean, not really exact. I don't think that they really determine some processes. It's not really clear what do they determine from everything, but some processes they want to determine based on this sentence. They just announced that there could be potential applications, but of course we will not going to read it and discuss it. And maybe it's true, maybe it's not. Let's leave it as a side comment, which is not important, because nothing is written here, it's just a citation. Some non-equilibrium quantum devices, yeah, maybe, but haven't seen any non-equilibrium quantum device yet. Even the idea of creation of it, which doesn't mean that it doesn't exist or no one is trying really to develop it, but here this idea is not explained. So let's go just further. Here they say that there is this Ising model which give us a motivation to use this programmer quantum annealer because they are relatively related. And here they say that there are some advantages of the classical anisotropic Ising model. And this anisotropic model is not really sufficient for the quantum regime. Maybe I confused and explained wrongly what they mean here. Maybe it means about the inhomogeneities. Maybe if we use just purely this model without any noise, maybe that's not enough to describe these domain walls. I guess that's what meant here. Okay, there is a second method, which is a Benicio method, maybe a collection of methods. Maybe it means that calculating something from the first principles. And they say that these principles are not used for simulation of collective dynamics. But I was trying to read one article about Benicio methods. Here they're presented in the negative context, that something they don't explain what they want to explain. Maybe by collection dynamics they mean such reconfigurations, but that's again not an exact statement, so we can only guess. But ab initio methods are not the ones that they prefer to use here in the article. And if we have non-equilibrium dynamics, that's even harder. And as usual, what they say, yeah, like the problem here is that they don't assume any particular model. That's an abstract statement about some simulations of some system. So if there are more than 50 qubits, yeah, the Hilbert space is big because it's 2 to the power of 50, but maybe we don't need all this Hilbert space. So it's well known that that's problematic to simulate quantum model in a classical system, but I can't comment you much why is it really so. Here they just say that if we have even non-equilibrium dynamics but not also collective dynamics, then that's hard to simulate. And if we have a lot of particles that I mean a lot of sites in the system, then it becomes even harder. Then there is the quantum Monte Carlo calculation, which is not developed right now. So another method doesn't work. Okay, and another method, and some simulations have been demonstrated. Is it important for us? Definitely no. But there is another method that exists there. Okay, they even don't even explain what does it really mean. Some simulations of ground states are there, so if you want you can read, of course, the cited paper. Yeah, so then they say that if you even want to use it for real world, so they have even problems with simulations, but if they want to use it for real world, then they need a lot of qubits, thousands of qubits. So they need to have a lot of control of the coherence and computational resources, which is similar to what was said before, because before they said that it's hard, currently unavailable, like to do such calculation, but it should be double checked because there are a lot of methods that are developed constantly. So maybe right now something is possible more than is announced here in the article. And about the decoherence, so they say also that it's like, I mean, you shouldn't take seriously this word control decoherence, because like it's obvious where it originates from, because if you do the quantum simulation you need to have everything coherent. But if we're not speaking, I mean, okay, it's written, this sentence is connected to this sentence about the quantum simulations, so this doesn't work. So they say, that's what they say, that here there is there are some simulations, but it has some disadvantages such as control of the coherence, and also these quantum simulations require a lot of qubits. And they don't say that it's impossible, but they say particularly challenging. And then they say that for 40 years some people are trying to discover something in the motion of domain walls. Then they say that there are some other cases where there are motion of walls. What is known about this motion of walls in other cases, I don't know. But there are some research and there are some measurements of these unrelated materials where there are also domain walls. That's irrelevant. Disordered ferromagnets, it's also irrelevant, and other materials have domain walls. That's a great thing. Maybe if I do like this it will be better, by the way. Okay, now finally we maybe we'll read something relevant. So maybe that's the important statement, that quantum noise driven domain walls dynamics. So before, let's look again. That's why I was not assured here. They say the context of environmental noise. So they announced that this change of fluctuations was because of the environmental noise. And here they say that the quantum noise driven. So I think that's like a contradiction, because or it's environmental noise or it's a quantum noise. So maybe we should think that all this dynamics is driven by quantum noise, but here there is environmental noise that gives us the crossover. But okay, there are some noises that are somewhere there. Anyway, they will use one of these two models where I don't know where noise comes into the game, actually, unfortunately. Maybe because of the device concept itself, that somewhere there in the quantum computer they have the like it's noisy one. So anyway, if they get some measurements, they will get it with noise, and maybe that's why they're not even trying to include the noise into this Hamiltonian. Okay. Okay, here they write something that answers my question, which I wrote half an hour ago, why exactly they use tantalum disulfide, and it's not clear which prototypical behavior. Of course, we can remember the article about tantalum disulfide from mod state to superconductivity by Sipos et al. And they have this phase diagram. Maybe they mean this phase diagram for the prototypical behavior, but it's not clear really. We could have chosen different other models, and it's also interesting that is this approach applicable to other models. Maybe other models have different decay rate, so it's interesting to understand what about other models. Maybe they will have different decay rate, and already this simulation will be not applicable to them. But also, as we see here, it's very strange that simulation stops here, but maybe later we will see some explanation of this. Okay, but they choose that they will use only this material for simulation, and they will try to fit parameters of quantum simulation to explain exactly this material. Okay, then there is the claim that is familiar from the previous stream, that kinetic term is reduced, Coulomb energy is dominated. That's why in this paper of configuration of electronical states they have only the potential term, because of exactly the same reason, but they don't have at all any kinetic term. Here they have kinetic term, but maybe they use similar citations and say that the potential term is way bigger. But again, they have this chemical potential term, which I don't even want to comment because I'm not sure of real origin of it. Of course, that's well known that it can be added or subtracted, but it's not like really a constant. It's a state dependent term. Like if we have some electrons here or there, they will be summed, and if we don't have them, they will be not summed. Okay, but that's what's written here, the familiar statement for us. Okay, then here there is maybe important statement for theoreticians like me that essential physics comes from polarons with variety of states. Yeah, so it means what we see here. Okay, there is, as I said, the discussion of why exactly do we have polarons here in this material, and here I don't want to go to this topic too much, but the idea is that like there is this theory of polarons, and exactly this theory is applicable, and these polarons are ordered always. They can be ordered, and there could be a domain wall between them, but the islands are only ordered. It's actually a good question, which I learned right now, that look like here we deal with this region, and that's this region, non-commensurate charge density wave on this plot pressure and temperature. So how do we go from this region to, yeah, okay, if that's important question. Okay, that's definitely a good question. Maybe the answer is that here, sorry, Okay, I got a better answer actually while right now thinking about it and writing the question. So maybe we are not in the non-commensurate charge density wave, but just in commensurate charge density wave phase, and we just inject more electrons. And when we inject more electrons, they like maybe like, so I mean, if we inject more electrons, why do we have domain walls smoothed? We get. Okay, so that's what I think right now, that here we have more energy than here because we inject electrons. That's how we get this state of the electrons where there are domain walls. So there are more energy in the system than it relaxes, and that's the typical commensurate charge density wave phase of this material, and this corresponds only to the purple region of this plot, so we are not dealing at all with all other regions. Okay, let's put it here, and So here they say just that there is a theory of tolerance which is applicable. So they cite some switching behaviors, and it's not clear how is it related here. So maybe if we inject electrons, there could be also some switching behavior. No, I didn't write question here, which is my because I overlooked this statement, but here they say that also there could be some switching, but I think it's irrelevant for this because here I don't think that we are working with switching. And again, they say that there will be a scanning tunneling microscopy. Again, they say about the topological inhibited processes, and I don't know what is meant here. But there is some... Okay, maybe it's a good idea to finally read this paper at least once, one of them, and find out what is the property of this classical dynamic, which is, as they said before, not applicable in any way. But it's good really to double check if it's applicable or not. Position quantum analysis. Okay, they again don't explain here, and they also repeat the sentence, so we can forget about both the sentences. The idea was explained even before, that they don't like, for some reason, classical processes. If you want to know, you can only go to the cited paper, because here they don't explain much. Maybe they shouldn't explain really, because that's a research article. It's maybe fine to just give a citation, but from this theory it's impossible to understand what they don't like, in which exactly classical model of dynamics. But again, the conclusion is the same, that they need some quantum dynamics, but in scope of quantum dynamics they also need exactly this one, not some quantum as it's written here. As it's written here, quantum simulation of ground state properties. So some cited papers are not also what they want to use or what they think appropriate for this material. Okay. Okay, they mention for the third time, as far as I remember, memory devices. So if you're bored, just mention non-violet memory devices. I could have typed in the search how many times have they used the memory devices word. Of course, they say nothing about like how useful it is, but man, if you're bored, just cite papers about memory devices, and that's all. Okay, now we're finishing finally introduction. Again, they write for n+ first time that they used the simulator. They used again statements of noise. Why is it okay? That's what I said, that all of this dynamics is because of the noise. What is this pink noise? In one place it's written the environmental noise, in another place it's written that is a quantum noise. Here we don't know because there are no formulas, but some noise is there. And maybe I was opening this paper a long time ago, simulation nature with nature. and yeah, like, but this classical computer nature, maybe yes, it's also a nature. It's a definitely philosophical statement which we might, I mean, I propose just to forget it. Nothing is really important here. They just repeats the sentence about noise. That's what I also wrote here when I was preparing this stream. Nature. And they announce again that they will have a very good result, and that's their very good result. The criterion is not written, but and also it's actually important question, really important question, which is written here, that if it simulates remarkably well, then why do we need some extra research? You just use this model because that's enough for this material, and maybe that's enough for other materials. You see, like, there are different configurations. Okay, maybe this potential can be just different for different materials, and that's maybe enough to do simulation of all two-dimensional materials. Of course, I don't see any reason for this model to be applicable because it's a mathematical abstract model which is not driven from some microscopic principles. But okay, that's how the model is created, and they just claim that the results are very good. Okay, let's just believe them. That's the repetition of the previous sentence. Okay, they again say that valuable insights. Okay, okay, I mean, like, of course there is nothing important here because they say just this model gives this result. Okay, what do we know about microscopic many-body interaction? Definitely nothing. Nothing is learned about it. Nothing is known about it. I mean, because that's the model, right? That's what they do from the simulation. I mean, you need to relate this model with this model. Unfortunately, right now, I'm not sure that it's explicitly written how to get this model from this model. But the idea is that, like, okay, like, from wave function, many-body Schrödinger equation with a lot of struggles and approximations, maybe you can get this. I mean, in general, you should be able to get this model in some limit, and then this model should be driven from this model. So if we use this model in experiment, we can go back and, at least on this level of tight binding approximation, or I mean maybe second quantized approximation, it's, yeah, okay, we have strongly coupled systems, so it should be a tight binding approximation. So how we can get some of these parameters? But if the system is homogeneous, then all these t's should be the same and all these v's should be the same. But okay, they also have explicit formula for v, which we will see very soon. But no, it's not really clear which insights it can give. If you know, then write in the comment. But here I tried to extract this information from this sentence, and no, it didn't work out. It's just an announcement, because, like, they could have written that this lead to this insight or that insight, but no, they just write some insights, so you can only guess which insights, which gives us motivation to think that there are no insights. That's what happens when I read this. Okay, so now we have gone through the introduction, and okay, that's the table of contents. They have two results, basically, the measurement and reconfiguration. Here they just say that one model is not applicable, and there will be discussion, but as I showed you before, the article is just 5 pages. Maybe around 5 pages, so it shouldn't take too much time. But at least that gives us really valuable understanding. So what we should know is that this material has square root over 13 over square root over 13 times square root over 13 electronic superlattice. And I am not sure about, I mean, that's definitely true, but I can't explain this square root over 13. I wasn't thinking about it. Some configurations of some number of atoms, and maybe if you count them, then you will get the number of 13. I don't know the origin of this size of superlattice, but that's how it looks like. That's the superlattice. Also not sure why they have only tantalum atoms as these gray dots, and why do they have such big electron? Okay, maybe electrons are wide, that's why they are so big. They also, as I wanted to remind you, dressed with the something. Okay, actually it's a good question. Okay, that's actually maybe a big not a big, like, drawback of this model, that if we speak about polarons, and we'll speak about polarons here because electrons somehow localized, and if they are localized, there could be different mechanisms, and other mechanisms are ruled out. So the only mechanism that is left is the polaronic mechanism, and polaronic mechanism is when electron attracts some lattices around it. But here we don't have this attraction, which is maybe a next order of magnitude effect, but it's a very valid question, like why do we speak about polarons if we don't have any distortion of the atomic lattice? And maybe the idea is that this distortion is actually not that big. Actually, it's a very good question. So the question is that, like, here we have polarons, and maybe they just tiny distorted, so maybe we will not even see this distortion of atomic lattice on this plot. And they have done already a stream about polarons, but that theory tells me nothing about how much distortion is because of this interaction of electron and lattice. They have some abstract formulas about polaronic radius, but okay, let's just forget this side comment, which few people will be able to answer. Let's look at the B plot. Here we see two lattices of polarons, and there is a domain wall between them because they don't coincide one with another, so they just sit there, and there is empty space which is filled by electrons. It's actually a good comment to think about later, that I speculated that if we introduce more electrons, then these gaps should be more energetic, because then it relaxes. But here we see the opposite picture, that the gaps are white. And what do they mean by white? It's not seen here, but we will read about it later. Okay, anyway, that's the two lattices. Here we have this experiment that I showed before. These are the parameters, which you can ask about also why we have these parameters, but maybe it's rather not important. that's the question for experimentalists, and maybe if we change current, maybe if we change voltage, we will get different results. But and I'm not the proper person to ask about it, because right now there are, it's a complicated question to have some theory about it, and this article tells us nothing about the current and the voltage. Sorry for this jump, that's because this app is not finished. Here we have that a function that will be introduced very soon, how many of polarons have jumped as a function of time. So as I said before, it's a very slow process. That's why we don't see this on this plot, because first of all, we don't inject any new electrons. Second of all, that's a very slow one. So I don't understand this inserted plot. It was claimed that that's energy, free energy as configurational coordinate, but I have no idea how did they get this very strange plot and how we should understand it. So, but I tried. I will guide you through the statements shortly. But and that's about this free energy, which can be written as a function of this configurational coordinate. But if we don't look at the inserted plot, this plot is rather clear how many, how the fraction of them which will be changed, how much of them will be changed. And look, a lot of them change, then not so much change, then more, then not so much, not so much, then more. It's like a plot of your motivation when you do PhD. A lot, then slightly lower, but there are some peaks when you have like conferences or some cakes. Okay, not, of course it's a joke for me. Okay, doesn't matter. So that's how this fraction changed, and they were doing a lot of measurements and carefully counting number of changed polarons. It's interesting that never, except several points, 0 polarons change. And that's what they call here. They also call this Hamming distance. I wrote here the definition of Hamming distance, but let's not go there. And I have noticed that we have been discussing this article for nearly 2 hours, and maybe it's a good hint that we should speed up. And okay, that's the free energy. And that's the relaxation. So that's the comment about the thing that I have discussed already. This is the definition of Hamming distance. And now there are informative statements that, okay, it's not clear what do they mean by this air of t. Some air of t is there, but they say that there are if there were which nucleation or coalescence processes. I don't know much about either of them, but there would be two these dependencies. And if we look at the plot, we see that they don't really coincide with the measurement that we have. However, this feed doesn't also coincide with this one, so maybe we need to do some another measurement, maybe of another material, or we should explain this peak, but nothing here is given to us in scope of this theory. So in order to understand this peak, I'm not sure that it's really possible, but actually this looks like not really, how we can fit it, right? This doesn't fit, this doesn't fit, this barely fits, this barely fits. Maybe we should have just a different plot for the fit. And here, okay, that's for the different measurements. So they say, actually, this, no, I don't, like, I had a question here that why they have such a big gap, and maybe that's because they don't measure anything. and they try to understand how the measurement time affects the rate, but then they measure here it. Why do they measure it here? If they have bigger times, the second measurement should be somewhere here and not here. Maybe they were too lazy to rescale the plot, I don't know. But also we see that there are, I mean, like there is a big error, right? Like this, if you don't measure it, I mean, you also start with different initial state. That's very strange, right? Like, okay, so I should give more background, like what happens in this figure. So that's about this little function f, which they call Hamming distance, but I don't know why is it called Hamming distance. I just know this definition, and they say that they averaged this number over scans, over a large number of scans. Maybe they write in supplementary information for how many scans, but I'm sure that they have done it for a lot of scans, because I mean, this should be a high quality experimental work. And that's how they get these results. So maybe they did this measurement for a very long time, for very many times, and man, that's exactly what is written here. And then here they say that classical processes do not really describe it well. However, quantum process does not also describe this well. And then also if they introduce like if they measure not directly each 10 to the power 3 second, but also they have 32-minute gap. So if we multiply 32 by 60, we will get less than 2000, and that's exactly what is written here. Yeah, but it's not clear why is it here and not here if it's less than 2000. But it's really not clear. Then they say that this is the result for the case of the different gap. But no, we see that the initial, and first of all, the axis is shifted. Here we have 0, here we have 0. Okay, that's just a bad display, because here it should be the initial value somewhere here. And that's the initial value, so it should be the same initial value, it's just a different scale, which is a bad feature of the plot, but it doesn't make the plot run. Okay, I figure out that they actually should be correct. It's not a mistake, it's just a bad way how they draw plot. Have drawn plot. The 0 is not in the same place, but there should be also the same hill, I mean same column here. Okay, then they say here that tip does not influence much the measurement. Actually, okay, today I'm actually rather tired because I wasn't sleeping my 8 hours. I was sleeping just 6 hours, so maybe we'll have exception of the stream where I will skip some statements and not discuss them in detail. But actually here there are good comments that there are different sources of noises. Here they say that somewhere there it's known that there is 1 over new noise. What does it mean by this noise, and what are the consequences? It's not known. But here, as you can see from the measurement, nothing is written about the noise. You just see this configuration rate. Maybe they just claim that if this rate is so, then we have this type of the noise. Okay, that's the question that I wrote initially, that delta t and txp, is it the same or no? And it's not clear from this sentence, because like direction of, okay, I got it, that this is the different, that the time how much passes from one measurement to another, and this is the duration of whole experiment. So there are different constants, and that's related to the definition, why we exactly need exactly this definition. But anyway, we just divide by some constant, and we have the little value here. I can't explain why we need exactly this definition, but maybe it's not needed at all, because that's just a constant anyway. Like tx is the constant, delta t is the constant. It should be the same constant in all of the experiments. Maybe okay, if we change the delta t, then it's not anymore a constant. I mean, if we do one experiment, that's the constant scope of one experiment, but then if we go to another experiment, it will be also changed. So there is some clever idea why we have exactly this definition, which I can't comment right now. And here is a preview of what is shown also here, as I announced, and the main result of the article. That's the temperature dependence of this R, which we have just seen. What is it meant by R? And they say that they can fit this with this model, like exponential decay and the constant. Is it a constant? Most likely no, actually, but yeah, I mean, maybe we should do another model. But okay, maybe there is some theory behind this formula that gives us a big understanding of what happens here. And okay, here there could be important questions, but I'm really sorry that today I'm more tired than usual, so I will skip them, and I'm not going to do another stream, because that's my conclusion, that I mean about this article, that I should not do the stream when I'm tired. Or maybe now, maybe I will push myself and finally analyze all this article, but I'm not going to analyze supplementary information. That's a 30-page document where there are a lot of technical ideas, and these are actually valuable ideas, and it's impossible to understand this article without that supplementary information. But this stream is already 2 hours, and I actually wanted to go sleep even 2 hours ago. So they say that this is the fit. This fit has two values, RQ and EM. This is RQ, this is EM. There is some activational energy. What do we activate? It's not clear, but this energy is the same, is in the same range. What is it? No, I mean, yeah, it's not in the same range. It's from 10 to 20, and that's from 3 to 9. And what is the experimental consistency check? It's not really clear, so they just apply this model, and maybe somewhere there is some energy which should be this energy, and maybe that means that this formula makes sense. That's how we can understand what happens here, and nothing can be learned more from what is written here unless we go to the cited paper. Then they have comments about this picture, that they have this plot. So and maybe that's an artistic plot of that free energy of the figure 1D, which I have just shown recently. Yeah, like of course this makes sense, but we don't know any formula for it, and that's why there are questions from me. So idea is that we always have a free energy for this system, and always if we have a system in one state, then there is a local minima which corresponds to the system. And that's a general philosophy of, I don't know, phase transitions or many body, like statistical physics, right? And they just write extra comments that this is the dimension, but dimension is the different parameters that are used, and because there could be some entanglement which is not discussed here at all, but in general this could be the dimension. And again, clear statement is that excited states within the main well, within the wells correspond, wells in this free energy correspond to process where F is conserved. So number of particles is changed by the same number, I guess. And that's correspond. Okay, maybe that what means that. Okay, there is the deep idea about which I don't really want to think right now, but maybe the idea is that if the same number of particles has changed, then yeah, but they should not go away from the system, so they should reappear. The system should has periodic boundary conditions, because we can't like really shift everything. If we shift, there is a boundary from which some new polarons should appear in the system. That's how I understand it, and that's how we will have the same delta F, and that's why we have a translation, and it will be the same state. That's why we'll just sit in the minima. That's how I understand it. Something like this was intended here, but it's rather unclear statement, and it's very unclear how did they get that plot, and at all how do they use this any function of the free energy. Okay, that's the idea of the introduction, of the first part about the measurements, that this is what they see, this is the parameter that they really interested in because they count, and also they oh, by the way, I forgot to say that main idea here is that the tip is not influential, so that 1 over nu noise, which is not explained, originates not from the tip. It's not clear if it originates from quantum fluctuations or environment or thermal fluctuations, or 3 of them, but here we see they conclude that it does not originate from the tip of the microscope. And okay, the details I skipped a little bit. In the quantum decay rate section, nothing is much here. They say that there is this known called the Yaroslav model. Right now I'm not prepared to discuss this model because I always was lazy to focus exactly on this model. Right now what is important is that they say that this model is not applicable. Why? Because it requires this value to be bigger than 1, em divided by h omega 0. What is em? I don't really remember, but let's try to scroll and search for EM. And as we can see, there is nothing which will help us to understand what is EM. EM is here actually. So this parameter that is not introduced, but it's fitted from experiment, divided by h omega 0, and h omega 0 is the kinetic scale of polarons. So you see like how it works, like some energy which penetrates this reconfiguration rate R. So this energy scale is compared with kinetic energy scale of polarons, and it should be way bigger than 1. I haven't heard that in this Caldera-Leggett model we are using the kinetic energy of polarons, but that's what's written here, that this parameter should be way bigger than 0. Again, reminder is that it's not clear what is EM, but that's the deep understanding of Caldera-Leggett model. And it also has some prediction, but maybe this prediction also doesn't coincide with what we measure in the experiment. But that's exactly what's written here in the quantum decay rate. Why is it called? Because maybe if we speak about this, where is that's actually there were other plots, which, yeah, this one. So maybe it's just the plot 2 of the figure 2, not on the figure 1. So that's also a sketch of the free energy, and if we have a quantum system with such potential, it can tunnel, and this tunneling is described by Caldera-Leggett model. That's why we can get the, actually, yes, look, it's confusing thing. F is what? F is just the number of picture, V is the whiteboard potential. Don't confuse this F, of course, with the Hamming distance, which was introduced before. So that theory has also this decay through the vacuum, and that's why it's called quantum decay rate. Would have been better to call it that. No, Caldera-Leggett model is not applicable. Why Kramer's is here, also don't know, because usually people call it Caldera-Leggett model, but I will look at it again. That's the main conclusion, that actually we just don't need this model, which again just motivates us to do our these quantum simulations. That's the essence of this third part, basically second part about the simulation. And so I will still run through all of what happens here. Here they say that this is the model. They don't write what is the potential, but I extracted it from the supplementary information. So that's the potential. This is the Q's as maybe I made a mistake. I thought that Q is CC, but no, Q is C dagger C, which of course that's what should be. That's like the number of particles. Okay, I didn't really understand this plot, which is introduced before we go to the plot of the main simulation. So here they claim that there are 3 ground states out of 13, as it will be said before. Why do they have these ground states as like this? Maybe because, like, if we fix this this cell, then there should be a polaron here, but no, there is no polaron. Or if we fix this cell, then there should be polaron here, but here no, and here also no. So where there could be another polaron, like if we come to this cell, it can be here or here, then it can be here. Let's look here, here or here. Yeah, so here or here, that's the green one. Here and here, that's the purple one. That we can actually compare it to this one. So that's only 3 possible ground states. Why will they write later that 13? I don't know. But yeah, that's how it works. It's actually a good question, that why do we have white place here? Maybe there should be more electrons, but I will just ask the author later. Okay, but right now I have understood that this is the ground state, and that's the result of experiment. What is the difference between these measurements? I don't know, but there are some values like r equal to 9, but as far as I remember, they will write that r should be 53. That's the value that I remember. So let's not ask right now the question why we have these parameters as t equal to 5 milliseconds. And one of the questions that I wrote, that this TA, does it, I mean, I wrote it when I was looking at this plot, that does it correspond to this t, which is 32 minutes, for example. And I just forgot in this plot, in the first one, what is the time, on how much do they measure. It should be 500 seconds, and here they measure each 5 milliseconds. Maybe it's milliseconds. I need to double check this notation. So why we have a different time, it's not really clear, but there is a text and there is a big supplementary information, so it could be still possible to run this. Now, there is a question which I wrote here, so I will just tell it, say it, and of course I don't have an answer at all. That before we had, like, of course you remember that decaying plot which was even fitted to the exponent, and here we have absolutely non-exponential plot without arrows, with some special peak. And of course there was also a little peak in the previous plot, but it wasn't such a big peak. So we'll get absolutely different results. It wasn't clear which parameters should we input. Like, first of all, to make it sensible. Second of all, to describe exactly this material, which is not explained, and it's not explained why exactly this material we have chosen. Why wouldn't we choose other materials also and check other materials? But that's the result from the simulation which they report, and they look very different. But they do rescaling or something else, and in this rescaling they come to this fit. So actually, if you manipulate this data, and also if you use this formula which is here, and if you find out what is the tx and delta t, then you should get this plot. That's what they announce, but it's not seen what exactly how exactly they use the values here. But okay. They do some rescaling, but they don't explain it here in the caption. Maybe we should go to the text, and text will explain it to us. But the text is rather big, and let me try just to extract key information, because I should have slept more before doing the stream. So that's the point where there are results, so they claim that this is the model that should be used. That's the decoding of the qubits to simulate this material, and this picture is the one that I did not understand at all. Maybe it requires some knowledge of the architecture, and there are a lot of couplings of the qubits. I guess that's what is meant by the orange lines. So this picture somehow tells us how we can use this model to encode this model. It's not explained here in the main part of the article how to derive this model from the previous one, and I looked at the appendix. There are, supplementary information, there are some formulas, but they also don't really, as far as I remember, explain this connection. Okay, then basically they say that, yeah, we're doing this simulation. Then they describe the simulation, then that they use changing of R to initialize a state, and then to do the measurement. So somehow they change the effective temperature and the R. And maybe they have a mistake that they didn't divide by KBT. Here it should be a division by KBT, because that's the same formula as before this one, but written for a particular value of T, and T is maybe the parameter that plays role of a time. Why this? Okay, I will write this question. Okay. It's not clear, but that's how I remember what happens here, that it plays role of a time, and they initialize the state, and they change this parameter in a clever way and get another state. So, like, you see that it's very hard to achieve these results. Like, you need to know how to program quantum computers. So, a lot of things are written here, and maybe here they describe the results, which are about this plot. And then, oh, I said like 53, it's actually 58. Reproduce experimental dynamics, they need this R. So maybe they got the right parameter that fits to this model and gives the result, the right behavior, this one. Maybe that's what they have been doing, fitting parameters to get the right behavior. So maybe if we do some theoretical derivation in a clever way, we should get this exactly parameter in this model. Maybe someone might write theoretical articles, hey, we are deriving the parameter of the programmable quantum annealer, which describes this material. But nothing is written here about it, and that's definitely not a good starting point to do this direction. They also say that, okay, we actually have Wigner crystallization, and that's the parameter from which I forgot to put comments actually in my text. Okay, from which there could be a Wigner crystallization, and Wigner crystallization kinetic term should be way less than the potential. That's what we also see here, that this R, which sits here, is a big one. So this is 31 times bigger than this one, at least, because there are also these values, but they should be approximately 1 and effect of chemical potential is not discussed. That's why I don't like to comment chemical potential, because it's often not discussed, and even if you comment it wrongly, no one will spot it and no one will punish you. Okay, now, so that is the main thing of this chapter, that this paragraph, that they provide us these results, and they do some technical discussion about how have they done the simulation. Also they have a discussion of the results of this quantum simulation. And we are coming to the section of discussion. I just wanted to scroll and see, yes, that's the last section of discussion. It's just 2 pages. So we are at the finish line finally, after approximately 2.5 hours. So they again return here to the Caldera-Alliget model, and there is some spectral function there in the model, which I forgot right now. I mean, I wasn't revising this model, but let me try to extract some useful information. So again, that's why I didn't understand this story about the noise, because suddenly noise appears again, and before nothing was written about the noise. They just claim that that's the noise, because maybe they just know that that's the noise. I'm not ready to extract some useful information from this part. Okay, they have some discussion of the noise, that like it could be a temperature, noise from temperature. It could be like, I don't know, like if we set limit of energies, we will have no noise. No, some abstract discussion of noises here, and their interpretation. I mean, I don't know, like really, there are some extra comments. And then there are comments about noise effect on quantum tunneling. So that's what they show here. That's what I remember. And I can explain right now that that's what happens with our potential for the qubit, and it was before here, but now with the noise we have a bandwidth, and system can go easily to the top of the band. But I'm not sure that we can really explain it with these words, but that's what they propose us, that somehow system can also easily jump here, and from here it's very easy, not so energetically forbidden, to jump here. That's why somewhere there they have some decay rate. Let's see their supplementary information. Yeah, that's supplementary notes. Yeah, here WQB approximation and mesoscopic quantum tunneling, but I don't want to click on this on this section, go there, but I just wanted to say that that's the origin of some quasi-classical tunneling, because here effectively somehow we also have a potential as a function of something. It's not written here what do we mean by Q, and I don't know don't want to guess, but somehow have this potential, and there could be some tunneling, and this corresponds to the state, so maybe that's a parameter space. And anyway, it's a schematic figure. These authors for some reason don't write explicit formulas about the free energy. Maybe I need to discuss it with them, because they definitely have worked with it, but they just don't write it in the article. I don't know, I'm not sure why. I would have written it if I were researching this topic. Okay, so here there is a discussion of noise. Here there is again discussion of noise. Here they say that noise actually increases the probability of tunneling. And I'm just trying to remember what is useful here. Okay, that's the part which I missed when I was preparing the stream, but I also don't have much energy right now, so I can't recall what is really useful here. So they say here that it emerged from device concept, so that's why they don't have any formula for it. And they relate the bandwidth with the configurational, how do they call it? Configurational coordinate. Why do they call it configurational coordinate? I have no idea, but that's what I remember, that it's called configurational coordinate. And so my conclusion is that here they have abstract, unclear statements about some connections which involve some extra understanding. For example, noise, they associate with parameters of the model that they discarded initially. So why do they write these parameters here? So they don't have any noise in their model. That's what I see from the formulas. I mean, there is the simulation, which is the only thing that is used. Okay, finally, that's the end. There are not so many things that happens in discussion, just around three paragraphs. The first paragraph tells us about the noise. Just I wanted to understand like what is really useful here. It's so strange that I was reading it like at least 2 times and I don't remember what happens useful here. I mean, that's obvious, right? Like we will have pure tunneling events, yes, because we'll have just purely quantum model. They again stick to Caldera Logaric model, but they have discarded it. Then they again repeat how they do the quantum measurements. Okay, I mean, I read it again, I don't see any value in everything here. Maybe I will ask an author of this paper and he will tell me what is the value of what's written here. It looks like very unrelated abstract comments, like when you see the text, but it doesn't make sense and you don't see value at all of this text. The only thing I remember is that somehow, like, we can glue two pictures of like this potential and the energy levels and say that electron can somehow be on this level, but if it has a fixed energy, then if it has a bandwidth, it doesn't matter, it will sit again at the low energy, it will tunnel with the same probability. For me, even this is not clear. So the delta means maybe difference from here to maybe here, but it's also not clear. What do they mean by delta? To level, maybe delta should be actually here. So, I mean, that's a collection of very unclear statements and they don't have any good conclusion from it. They just discuss the bandwidth, repeat some comments about configuration coordinate. They say that they extract this barrier width and the barrier energy. Okay, but that's in scope of that model, like it's not related to other models by default unless you tell us how is it related. Here it's not related. It's also interesting how to extract the barrier width from all of these experiments. Maybe we need to like solve this problem of this configurational potential and get the probability of tunneling and then compare to it, but for me it's very surprising that we need exactly this value, and this value has this division of measurement times. So some advanced theory is used here, and they tell us that they extract bandwidth and energy barrier because maybe it will give us some useful thing. So, but as I said, nothing is useful here. There are just comments for your personal development and for your broader knowledge. What happens with noise. Like each polaronic site is split by h omega alpha into two levels. Why? Like, I mean, just because like one of the proofs that nothing is important here, like read, like each polaronic state is split by h omega alpha into two levels by adding the h omega 0 degree of freedom HO harmonic oscillators. Like, why? Like, yeah, I mean, there is a spin splitting which is neglected everywhere here. I mean, oh yeah, I remember I was reading this. So the idea is that there could be two levels, and we can they might be splitted by h omega alpha. But what is h omega alpha? Yeah, like we don't have a splitting, unfortunately. It's different coordinate, different configurations. Tunneling between them is possible by default. We don't need any splitting for it. So no, I don't think that that's a good theory. We also have again C alpha, M alpha, omega alpha, which are there in the spectral function, but how this spectral function is related to the model, it's not clear. Yeah, we can read articles about Caldera-Leggett model, but that's not related to this programmer quantum annealer. That's my conclusion. And finally, we have done it. It took us 2 hours and 40 minutes. Let's just look shortly on the supplementary notes, because maybe I missed something. Here they discussed, I mean, I definitely didn't miss anything, but I just want you to see the whole article, not to keep something in secret. So they discuss the experimental tip about experimental STM technique, again experimental STM technique, which I will maybe never read because I'm not experimentalist. Again experimental part, and again experimental part. And now there is more important thing, that how to, okay, maybe it's also more experimental part, but it's related to the calculation of the most important parameter f. And here there are some formula for the f, and then they have a formula for the reconfiguration rate. I think it's really important to understand this in order to understand how they got the main parameter, but some not easy method was used here. And I'm not prepared to discuss this method. It's a rather technical one. That's obvious definition, like the same as here, but I mean, it's a good exercise, but for really fans of this article to do some calculations, at least one calculation on their own. I don't think that there will be ever a person in this world who will see this article and do this exercise. But if you really want to do something similar, then that's essential part to understand how they have been counting these properties. They have scheme of the evolution. They also have scheme of the polaronic sites in like different coloring. I don't think that that's the useful image. This is experimental image, which has strange scale, and now we see like PM. What is PM? Okay, I don't know why we have like increasement of some parameter, then it decreases to very little value, but there definitely should be some explanation. But this is the plot that you can see here. Then they discuss temperature dependence of the rate, which is an important actually parameter, right? Yeah, actually here, that's what I said, that this rate is calculated for different temperatures. So each point was obtained for the, maybe I didn't emphasize it, I'm not sure, but the rate is a function of temperature and f is a function of time. So to get the function of temperature, we get the reconfiguration. No, we get, okay, the configurational coordinate. Yeah, okay, they also use a very uncomfortable notation. Like they could have said like fraction of moved electrons and not say configurational coordinate or Hamming distance. Is a confusing statement. So they do this for the different temperatures, and that's how they get the. Okay, they should have gotten this plot. These are the comments about this plot, which are of course essential, but we don't have time for this. It's better to remember just this plot. And these are the comments about these plots. And now there are details about the tip. Again, the experimental part. This is the current. This is the voltage, because of some clever reasons. And unfortunately, it's not written here in the comment to the caption to this plot, but I guess that's the configuration rate. You start from this setup, then they go to this setup. Because time passes or some quantum fluctuations. Okay, another measurement, I guess, is still present here. Then they go to the that thing, remember? Let's open it in the results. See how I do it? I don't scroll much because of this beautiful application. So they look at this plot where they have different times of measurement. So this is what they do. They don't measure, then measure, and that's how they got this plot, as far as I understand. And we see explicitly what is the image that corresponds to this plot. Maybe this is similar to this thing, that this is how it changes, so we can see explicitly this dependence. And they get some ideas from this. So maybe this is just more detailed theory for these plots. Now there are some ideas about this Wigner crystal and limit of applicability of the theories that deals with RS parameter. I should have studied it before, but I'm not sure about this thing. Then there is this famous discussion of this model, which they believe to be the true polaronic model, but it's a complicated model. It's not clear how to work with this model at all. What are the parameters to input? We have a lot of frequencies of phonons. We have spin indices. We have some lattice, which is not clear which lattice, since the actual atomic lattice is distorted. But in the famous book about polarons, this model is introduced, and we can discuss it later also. But they say basically that this is the initial model. After clever mathematical transformation, we get this model where there are new parameters, and then there is this hidden jump to another model, so they don't explain at all how to get this model from this model. So this is a nice theoretical, of course, discussion, but it's not the correct one, because this model is not derived from this model. At least right now I have no idea how to do it, and I have discussed with several people this connection, and there is no such connection. Just common sense tells us. I mean, there are some research is done about this model, but it's hard to deduce some experimental results from this model, and that research does not give us the derivation of this screening model. However, we'll approach this again and try to figure out these polaronic models. Right now I'm just focused more on these experimental articles or the simulational articles. Okay, that's the model that they got. And then again, they jump from this model to this model, because that's available on the supercomputer, and this model is not available on the supercomputer. But maybe that's the explicit transformation of the this model without kinetic term. So maybe they have neglected the kinetic term at all. That's what I guess, based on what's written here. But in the article itself, it's written, like, remember, here they explicitly say that there is a kinetic term, but here they write it without the kinetic term. And here they have this d-wave Hamiltonian, and that might be a good question. Where did the kinetic term disappear from this model? But anyway, there is this model. They map it to the d-wave model, and that's their starting point for their clever simulations of quantum computer. Now they have also classical Monte Carlo simulations. because they know how it works. Why not to try it? Maybe I will read this chapter again, and because of some classical simulation which it's better not even to try to understand, we got this dependence, and this depends on how many polarons have moved. And then they do some advanced plots based on that simulation to get some data which is not, as far as I understand, used in the main text, so it's not clear why they are doing this at all. Maybe to compare the results with D-wave simulation, and then they say that Monte Carlo simulation is highly inconsistent with experimental observation. So that's maybe the most important part of this paragraph, that Monte Carlo is not consistent, and if you want to know why, you can look at these results and compare them, and that's a nice research to see that something definitely doesn't work and understand why exactly it doesn't work. Maybe they comment why exactly it doesn't work here. And they also claim that this quantum simulation can't be reproduced by Monte Carlo simulation, which is also available statement, because some people might say, let's do Monte Carlo simulation. No, like the D-wave simulation will give results that are not reproducible in Monte Carlo simulation. But then there is a question that, like, is that the problem in the model that is plugged to the Monte Carlo simulation, because that's the model that is plugged, or the problem with the simulation itself? Maybe you should do it in a different way. But yeah, okay, one of the reasonable questions is that maybe you need just to modify this model, plug a more clever model. But more clever model, does it correspond to the D-wave or not, even if it's not clear if this model corresponds to D-wave simulators? But okay, that's the like valuable discussion of what if you go to the path of Monte Carlo simulation. Then there is the double QB approximation of the tunneling, because you remember that potential, and maybe if you understand what really happens, then you can use the formula for tunneling. But that's not the case for me. I don't understand where there are these potentials, so I don't know where is this tunneling. And here they I just know the sentence that Kramer's theory cannot explain the relaxation dynamics. It's not clear why for me, because I don't know what is a quantum Kramer's theory, but you can read this and see that it's actually a waste of time, because anyway it's not usable, but for general education it could be a good idea. And as I announced, the supplementary information is 37 actually pages, but with a lot of pages for references, so around 30 pages are there for the unique information. So that's why it takes us for such a long time. Now there are details of where are we here? We are here actually, yeah. So it's not left alone. It's not so much thing has left to discuss. So in coherent macroscopic tunneling, and that's actually, I think, one of the most valuable parts of the whole supplementary information, where they discuss the noise, the tunneling rates, they give advanced formulas, which I looked once, but not prepared to discuss what they really mean by this incoherent macroscopic tunneling. But that's like an important theoretical appendix as far as I see it now, with a lot of new parameters, unfortunately. So to understand this, I would need to understand a lot of extra things, and that's like activity for at least 1 hour. It will not take me less than 1 hour to really understand what happens here, even on the level of statements. Okay, finally, the third of the 4 supplementary information, they discuss here the D-wave simulation, and they say that there are some mapping, which is a clever one, which gives us maybe these 2-dimensional sites. How does it work? I have no idea, but yeah, some mapping is used. And there is the reverse annealing, which is a special technique for the device simulation. And I don't know much about it, but if you want to know how to simulate in quantum computers, that's the guideline, I mean, the proper comments about it, do the reverse annealing. And it's actually written in the text something about this annealing. Why is it needed? Maybe because otherwise it's not working. But that's interesting only for people who want to reproduce these results on quantum computer. Now the last part of the supplementary information, limitations by the annealer on the parameter space. And okay, what I understand is that there are just some limitations of this model, and I have no idea what happens next. And also there are phase diagrams, calculations. So they have done really a very big job where they have analyzed a lot of things that I have no even idea what do they mean. So they are really big experts in quantum simulations. But there were also like a lot of authors here in the article. So that's what happens when a group of big authors unite to do some research. Research becomes very big. And some relaxation measurements. So these are advanced plots which are obtained from the D-Wave simulators. A lot of relaxation rates, so they were just sitting and plugging this like quantum computer with a lot of tasks, with a lot of quantum algorithms. And they got some average rate of polaronic movements, which maybe is used further to obtain these two basically plots. This okay, everything is about this plot actually, but to get this plot you need to have f, so you struggle a lot with f. Maybe this plot tells us this, but maybe once I'll discuss something about it with someone. And okay, that's just supplementary plots to get this plot. That's how I understand it, and the relaxation measurement is again something about that plot. So if they have used that function with the exponent, that means maybe there is a strong reason, which you might see from here, but that's already a lot of information. And that's all. They have some discussion with reviewers, some answers, which is a nice, pleasant thing to read, which I have done partially, but it's a really nice, pleasant to read. I have my own lot of questions. And that's what happens in this article. So finally, after 3 hours, I want to announce that that's the end of the stream. It was a long one. I did not explain everything, so let's just look at the final results. So the finally, again, as I was saying several times, that's the measurement of one material. They say that, oh, maybe this model will be applicable, but other methods of working with this model are not working because we have analyzed them or we have tried them, like Monte Carlo simulation. That's why we will just use an advantage of quantum computer, which will give us something that we can't do another way, because, like, for example, I can't do this another way. But I don't know these parameters actually which they need to use to describe exactly this material. So I think they also feed this parameter from the simulation to make the simulation working. That's why I don't see that there are some useful insights about the material, but there are a lot of insights about how to do quantum simulation, quantum computer, and we see that people were working very long time with the simulations. And in the result, they got this parameter rate as a function of inverse temperature, and they connected with some parameters of the system, but these connections were very unclear, and the physical result is missing. But maybe if I have spent extra 10 hours, I would be more prepared and tell you more advantage. But also my main understanding was based on the article itself, not on the supplementary information. Here, to understand the article, except things that are very unclear, you need to read the supplementary information, which is a 30-page document. So that's really too much. I haven't ever planned to read such a big papers. Even like I also maybe not need this paper. I need to just be aware of what happened here. And okay, now I am aware. I have my own understanding, my own opinion. I don't think that all of the sections are really useful. Some of them look like a collection of strange abstract comments, but there is a big supplementary information, so maybe there is a big value in these comments. But also I feel that actually the big part of supplementary information is about the quantum simulation to get this very complicated plot. And maybe these comments are not related to it. But that's the best thing I tried to, I mean, that's the best understanding I could got from the reading this paper and trying to use my focus structure tool. If it were developed more, I would have AI chat here, but there is no AI chat right now, and there is no one who is developing this AI chat. So that's what happens. Yeah, so that's the end of the stream. Thank you for viewing it if you're going to view in the future. So we have learned that it's possible to do some quantum simulations, that they give results which classical simulations can't give us. They give some reconfigurational plots. And what else have we learned valuable? There are some microscopic models that have some parameters that make sense to have them, and it makes sense that these models have such parameters. There are a lot of questions about all of these models. For example, it's not clear how to derive it, or what useful knowledge at all do they give to the science. Yes, we can struggle with this modeling, but like telling that there are memory devices is not a good motivation at all, like to do this research. So maybe it's better to read the cited paper about memory device to understand what is the value of this work. But that's like quantum technologies, and I have learned a lot during reading this article. That's the main conclusion, basically, that like we can struggle a lot with quantum computers, but if you master this and adjust parameters, you can get, for example, reconfiguration of domain walls. Maybe something else is also done on quantum computers, but to understand it, we need to read other articles. So thank you for watching. I hope it will be useful for someone, and see you on the next stream. Bye bye.